All right, so today we're going to start Chapter 2. Okay, Chapter 2 is on reasoning. We're going to start out with what's called a conditional statement. Okay, so a conditional statement is a statement that is true some of the time, depending on the condition. Okay, and a conditional statement has two parts to it. Okay, the first part of a conditional statement is called the hypothesis. And the second part of the statement is called the conclusion. Okay, and a lot of times what we'll do is we'll write a conditional statement in what's called if-then form. If we write it in if-then form, it makes the hypothesis very easy to find in the sentence and the conclusion pretty easy to find. Okay. So I'll give you another example in a second, but an example of a conditional statement would be if it is sunny outside, if it is sunny, then I go outside. Okay, the part that comes right after the if in what I just said, that's your hypothesis. So if it is sunny outside, it is sunny outside. That's the hypothesis. Then I will go out. I'll go outside. That's the conclusion. So the hypothesis, it is sunny. Conclusion, I go outside. Okay, so whatever comes after the if is your hypothesis. Whatever comes right after the then is the conclusion. If you have a statement that's not written in if-then form, then it can be a little tricky to figure out what the hypothesis and conclusion are. We'll practice that a little bit. Okay, so that's the general setup of a if-then statement. If whatever follows right here is your hypothesis, then, and then whatever comes after that is your conclusion. Okay, any question about the general setup of an if-then statement? Here's the example that I just gave you. It says, if it is sunny, then I will go outside. Okay, all I'm going to do here is I'm going to identify the hypothesis and the conclusion. Okay. Anybody think they can tell me here what is the hypothesis? Ian?
Sunny.
Yeah, it is sunny. There's your hypothesis. And what about my conclusion? Owen?
I will go outside.
I will go outside. Any questions on identifying those two parts? So we're going to get into this more later on, but when we write sentences in if-then form, eventually we're going to want it to be more symbolic. Okay, I'm going to just use a little bit of symbols here to avoid having to write out an entire sentence. But in this sentence, P, because it comes right after if, that's my hypothesis. Q is my conclusion. Let P and Q be variables that represent sentences. It can be anything you want. There's different ways we can write an if-then statement. Okay, this is one. If P, then Q, whatever P and Q represent. We can also write Q if P. Logically, using logic, Q if P is exactly the same meaning as what is above. Okay, so using the example I had up above, if I said to you, I will go outside if it is sunny. Logically, that's exactly the same thing as saying, if it is sunny, then I will go outside. Okay, so this starts to get into a very technical kind of wording. Okay, it is very specific on how you say things. Okay, and here's a third way, and we'll get to this one probably a little bit later in chapter 2, that's also logically equivalent to the other two. Using my example, this would be like saying, it is sunny only if I will go outside. Okay, so three different ways, but they're all logically equivalent. Here's something that's not logically equivalent. If I said, if I go outside, then it is sunny. That's not the same thing as the other three. Because what I just did there is, I took the if-then form, but I switched the hypothesis and conclusion. Okay? You might say, well, didn't you do that here? Q if P? No, there's no then there. Taking out the then makes it very different. Okay, so as we go through this, I'm going to be particular on how you say it, or how you write it. So any questions on these three different ways to say the same thing? All right. So here's an example. It says, rewrite the following conditional statement below in if-then form. It says 2 points are collinear if they lie on the same line. Okay, I'm going to put up what we had on the previous page because that might help a little bit, especially the stuff at the bottom. Okay, the structure of this sentence. Which one is it most, let's call this one 1, 2, and 3. Which one is it most similar to? 1, 2, or 3? And if we can figure out which one it's, well, our goal is to write it like number 1. So it's not number 1. It's either similar to 2 or 3. And if we can figure out which one, then we can translate it into if P then Q form. Connor?
If 2 points lie on the same line, they are collinear.
Okay, so you're saying it's similar to?
The third. No.
Not the third, because it doesn't have the words only if in it.
If 2 points lie on the same line, they are collinear. It would be the second one.
So yeah, it's very similar to the second one. Okay, the structure of this sentence is something if something. Something if something. Now we just have to put them in the right order. Okay? So if we write it if P then Q, what's P in the sentence again, Connor?
Oops. No. Yeah. If, no. 2 points are collinear. So if they lie on
It gets a little tricky. Sometimes you have to add a word in to make it make sense. Like, see in this part, I use the word they.
yeah.
Since I use the word they, that's referring back to something I've already said, like a pronoun, okay? He or she.
2 points are collinear.
Okay? So we might have to, if we're going to write this part first, which is what ends up happening, in the Q if P form, what's at the end of the sentence ends up coming right after the if. We might have to specify the subject. We can't say they lie if they lie on the same line. If what lies on the same line? If 2 points. If 2 points lie on the same line. That's the ending part. P, which goes right after the if. Then, now I can use the word they. So how would I finish this off? If 2 points lie on the same line, then then they are collinear. I can use the word they because I've already specified my subject in the first part of the sentence. So that's how you take statement A and change it into if-then form. If 2 points lie on the same line, then they are collinear. Okay, the second one. It says, all sharks have a boneless skeleton. This one's a little different. So in this sentence, what has a boneless skeleton?
All sharks.
Sharks. So it's only if the creature we're talking about is a shark. Okay? So that's what we have to say up front. If the creature, or in this case, why don't we just be more specific and say fish. So if a fish is a shark, then this statement is true. Okay, so if a fish is a shark, then, and now I can use the word it, because I've already specified my subject at the beginning of the sentence. Okay? Or I could write the word fish again. If a fish is a shark, then the fish has a boneless skeleton. Okay, so there's a couple ways you could do it, but I'm just going to say, if a fish is a shark, then it has a boneless skeleton. Okay, any question on that? Okay, so that's how you translate that one to if-then. And the last one. A number divisible by 9 is also divisible by 3. How would I write that in if-then form? A number divisible by 9 is also divisible by 3. Okay, I'm telling you, this is a true statement. So you have two ways you can think about it. If divisible by 9, then divisible by 3. Or if divisible by 3, then divisible by 9. Think about which one makes more sense. One of those is true, one of them isn't. Yeah?
If a number is divisible by 9, then it is divisible by 3.
Yes. If a number is divisible by 9, then now you can use it, because we already know the subject. It's the number. Okay, so if a number is divisible by 9, then it is divisible by 3. So if you take the number like 18, 18 is divisible by 9, 18 is also divisible by 3. Okay, but let's take a number divisible by 3. 6. Is 6 divisible by 9? No. So this statement isn't true if you switch the hypothesis and conclusion around. Okay. Some statements are. Sometimes you can switch the hypothesis and conclusion and it's still true. Sometimes you switch it and it's not true. Okay, we'll talk about that. Okay. So tying in with that idea of true or false, I can give you a conditional statement that's either true or it could be false. It's very difficult to prove something true. Okay, to prove that it's true, you'd have to prove it true for every single possible case. So if we look back at the last example we just had, if a number is divisible by 9, then it is divisible by 3. If I asked you to prove that, which that's more of a college level thing, we're not going to prove mathematically that that's true. But right now you might think about, well, I'll just show it works for 18, show it works for 27, 36, 45. Well, unless you're going to show it's true for every single number that's divisible by 9, every number, from negative infinity to positive infinity, it doesn't prove it's true. So proving it true example by example, very difficult, because you have to prove it for every single number there is. But how about to prove something false? If I gave you a statement and I said, prove to me that this statement isn't always true. How many examples do you need to prove something is false? Yeah.
Just one.
Just one. Okay, to prove that something doesn't work all the time, you just need to show that it doesn't work at least one time. Okay, and that one example that proves something's not true, we call a counterexample. Okay, we call that a counterexample. So a counterexample to this last one, if I were to switch the hypothesis and conclusion, if a number is divisible by 3, then it's divisible by 9. No, 6. 6 is divisible by 3, but not by 9. That would show that that statement doesn't work. But that's not the statement we had. Okay, so I'm going to give you an example, and I want to know a counterexample that proves it false. So I'm telling you that this statement is not true. If x squared equals 16, then x equals 4. It's not necessarily true. Look at it for a second. See if you can find another value for x such that when you square it, you get 16, but it's not 4. There's another one. Anthony?
It could be -4.
Right, it could be -4. Okay, so x could be -4. And -4 squared is 16. So this is a counterexample proving that this statement up above is not always true.
All you have to say is that it could be, with any ifs or maybe.
No, because it just said write a counterexample. So there's an example. That's all you have to do. Yep. So if you can find a counterexample, proving something's false is very easy. It's very easy. Any question on that? Now, let's suppose we switch the hypothesis and the conclusion. If x equals 4, then x squared equals 16. That's a different statement. If x equals 4, then x squared equals 16. Is that true? That's always true. Yeah. If x is 4 and you square it, you get 16. So by switching the hypothesis and conclusion, I took a statement that was not always true and made it so it is always true. Okay? And there's a name for doing that, which we'll talk about. Okay? It's called the converse. If you take the hypothesis and the conclusion and you switch them, you just formed the converse of the original statement. So I'm going to write it out symbolically rather than using an example, but let A and B be any sentences you want. So let's say your original statement was, if A, then B. What would the converse be? Of if A, then B. Well, Sarah? Hey, here's your hypothesis, here's your conclusion. Switch them to get the converse. If B, then A. So just based on the examples I've already done, is the converse in the original statement always logically equivalent? Think about that last one we did. If you switch the hypothesis and conclusion, do you always get a logically equivalent statement? No. In fact, I took a statement just a minute ago that wasn't true and made it true. So the converse and the original statement are not logically equivalent. They're different. Okay, for this one, I just want to know the converse of that statement. If two segments are congruent, then they have the same length. not particularly asking if it's true or if it's false. I just want to know what the converse would be. Yeah?
If two segments are the same length, then they are congruent.
Yeah. If two segments, you notice how he didn't write they? That's perfect. Can't use the word they till the second half when you've already specified your subject. Okay. So if two segments have the same length, then they are congruent. Is the converse true? Now I'm asking you. Yeah.
Yes.
Yeah. Okay. The original is true, and the converse is true. And the reason that happens here is because this is a definition. This is basically the definition of what it means to have congruent segments. They have the same length. Definitions, if you write them as an if-then statement, are always true in the original way and in the converse. A definition is always true in both directions. Okay, so another type of statement we can get is called the inverse. Okay, the way we get the inverse of a statement is we find the negation of the hypothesis and the conclusion. A negation is just when you put the word not in. Basically, change it from being a positive statement to a negative statement. So if my original statement was, if A, then B, the inverse, I'm going to put the word not in the hypothesis and in the conclusion. If not A, then not B. So I'm going to take the same example we had last time. If two segments are congruent, then they have the same length. And I want to find the inverse of that statement. Okay, so usually we insert the word not. Sometime if we have a verb that means the opposite of the verb we had, we can use that too. Like here, if two segments are congruent, well, we could either say not congruent, or if we had a word that meant not congruent, a new word, we could use that word instead. Okay, so what would be my inverse of if two segments are congruent, then they have the same length? About Nathan?
If two segments are not congruent, then they don't have the same length.
Exactly. Yep, that's it. Okay. If two segments are not congruent, then they do not have the same length. So for this one, we don't end up switching the hypothesis and conclusion. We just put the word not in. Any questions on finding an inverse? Okay, and this statement is also true. If two segments are not congruent to each other, then they will not have the same length. And the third way that we can rewrite a statement. So we've got converse, inverse, the contrapositive. Okay, the contrapositive of a statement is basically found by doing the other two transformations of the sentence together. First find the converse, then take that and find the inverse. So you just do both of them at the same time. And that's the contrapositive. So anybody think they could tell me, using if A then B, what the contrapositive would be? So find the converse of it, and then find the inverse of that. Katrina?
If not B, then not A.
Right. If not B, then not A. Where A and B can represent whatever you're talking about in your particular example. Okay, so we'll do the same example one more time. So you can see all three ways of rewriting the same sentence. Okay, I'm going to come back to the one I have. Maybe we'll do that one after. So it was if two segments are congruent, then they have the same length. Let me just copy that. So that's the original. And now the contrapositive. How about Sarah? Could you give me the contrapositive of the original statement?
I'm not sure.
Okay, what are the two steps you have to do the contrapositive? First thing you have to do is find the,
Converse.
so you find the converse. So we're going to switch the hypothesis and conclusion. And then what do we do with the converse?
I don't know.
So first find the converse, and then find the inverse of that. So what's going to end up right after the if we switch, let's just switch the hypothesis and conclusion. It will say if
I don't know.
okay, what's my hypothesis right now?
If two segments are congruent, then they have the same.
Okay, just what's just the hypothesis?
If two segments are congruent.
2 segments are congruent. Yeah. Okay, and what's the conclusion?
They have
They have
the same.
the same length. So when we do the converse, the end of the sentence comes to the beginning. Okay? And when we find the inverse, we say not. So we're going to take the end of the sentence, put it at the beginning, and say not. So we take that part. Denver?
Between have and same, reading about
If 2 segments are congruent, then they have same length. Yeah, the same length. So what, Denver, what would be the first part of my contrapositive?
if they have
If 2 segments. So make sure we specify our subject. If 2 segments
have the same
have or do not have?
oh,
Do not have. So if 2 segments do not have the same length, then, Connor, can you finish that up?
They are not congruent.
Then they are not congruent. Yep. Okay, that's your contrapositive. Questions on inverse, converse, or contrapositive? All right. So I mentioned this term before, equivalent statements. If you have 2 statements that are either both true or they're both false, we say that they are logically equivalent. An example I gave you from the last 3 we just did If two segments are congruent, then they have the same length. The original and its converse, in that particular case, happen to be logically equivalent. They're both true. They're both true. An example where this doesn't work is the one that I did, if x squared equals 16, then x equals 4. That was false. But if you find the converse of it, if x equals 4, then x squared equals 16, that's true. Since one statement's false and one statement's true, in that case, the original statement and its converse are not logically equivalent. They're different. Yeah.
You just covered what I was about to ask.
This is something that is, this is a fact right here. This is always true. The original statement and its contrapositive are always equivalent. Okay, the original statement and its contrapositive are always equivalent. So that means if the original statement is true, then the contrapositive is true. If the original statement is false, then the contrapositive is false. Okay? So an original statement and its contrapositive are always logically equivalent. Always. Yeah?
Is there any situation that it won't be equal, like the same?
No. Nope. If you give me an original statement that's true, its contrapositive is true. If you give me an original statement that's not true, its contrapositive is also not true. Yep. This always holds. There's no exception to this rule. Okay. Does everybody have that? Okay, why don't you take a second and try that one on your own. See if you can write the three versions of that sentence. The inverse, the converse, and the contrapositive. So the original statement is, if there is snow on the ground, then flowers are not in bloom. Okay, let's start off with our converse. Okay, who can tell me what the converse would be? That, Eric?
Flowers grow, not grow, there is no grow.
The flowers are, so you said grow?
Yeah.
All right, we'll try to stick with whatever, like verbiage they use in the sentence. So can you just change that to the verb that they used?
Flowers do not bloom.
Okay, so if the flowers are not in bloom,
Yeah.
so that's your first part. If flowers not in bloom, then
Well, I put the flowers will not bloom if there is no bloom.
yeah, go ahead. Say that second part one more time. I think you got that.
If there is snow on the ground.
Not quite. So we can't have if at the end. So we have, if the flowers are not in bloom, then, yep,
Then there's no.
then there is snow on the ground. Okay, so it's a little picky, but just make sure we can't use the word if at the beginning and the end. We got to use if, then we got to use then. Okay, so that's my converse. Okay, inverse, a little bit tricky here because we already have a not in the second part. So what would happen there? Owen?
I said, if there is no snow on the ground, then flowers are in bloom.
Okay, if there is no snow on ground, then flowers are in bloom. That's true. Yep. Are in bloom. We're not debating whether or not these sentences are true or false. We're just finding the inverse, the converse, contrapositive. Yeah?
There's another way of writing that one.
Um,
It said if the flowers are in bloom, then there is no snow on the ground.
Well, with an inverse, you've got to keep the snow part in the first half, and you've got to keep the flower part in the second. So we can't switch the hypothesis and conclusion with an inverse. But you could say if there isn't snow on the ground, or, there's really not that many other ways to say the first part. The flowers are blooming. I mean, you could say something like that, or flowers are in bloom. But just minor variations on that. Okay, and the last part, contrapositive. Okay, what I like to do to find that is just go back and look at your converse and put the word not in. Or cancel the word not out if it's already there. Dakota?
If there are flowers in bloom, then there's no.
Okay, so if flowers are in bloom, then there is no snow on the ground. Yes? And there is no snow on ground. Okay. So the next thing we're going to look at, I'm going to put it up, okay, but it's all on page 73 in your book. Okay, so I'm not going to leave it up very long, but it's all the point, line, and plane postulates we've already studied. Except now we're going to take, maybe I'll do one of them and put it in if-then form. Okay, so one of them we studied is, through any 2 points, there exists exactly one line. A line contains at least 2 points. And again, they're all on page 73. If 2 lines intersect each other, then there is exactly 1 point where they cross. This one's already basically in if-then form. Almost. Through any 3 points that are not in a straight line, there exists a plane. A plane contains at least 3 non-collinear points. You might notice kind of a similarity between these two and the first two. Does anybody see the relationship between, through any 3 non-collinear points, there exists one plane? A plane contains at least 3 non-collinear points. They're almost like the what of each other. Not quite the same, because we've switched the order around a little bit.
Converse.
They're like the converses of each other. It's just not written exactly the way it should be to be a perfect converse. Same thing here. Through any 2 points, there exists one line. A line contains at least 2 points. They're very similar. And then the last two, if 2 points lie in a plane, then the line containing them lies in the plane. If 2 planes intersect, then their intersection is a line. Okay, so these are all postulates we've already studied. I'm going to take 1 or 2 of them and put them in if-then form. Maybe just one. Let's just take the first postulate, and we'll rewrite it in if-then form. Through any 2 points, there exists exactly one line. There's a couple different ways you could kind of word it, but it's still going to basically be the same idea. Yeah?
If there are 2 points, then there is exactly one line.
Yeah. So if we have 2 points, the only thing we have to do is be slightly clear about 2 points, and I think they even should have been clearer about it in the postulate, but the points have to be distinct. If you had 2 points like that, those aren't distinct. They're the same point. Okay, so I'm going to make that clarification here. So if 2 points are distinct, meaning not the same, if 2 points are distinct, then there's exactly one line that goes through them. exactly one line passing through them. And we could take any of these postulates and rewrite them in if-then form. Okay, this part does take a little practice to get used to doing. Okay, any questions on that?
Were you saying the plane passes through the form? Or were you saying that you-
Which one? Let me just put up the homework, Denver, and then we'll take a look at it. Okay. So the homework is on page 75. Okay, it's 1, 5, 9 to 21, just the odds. 22, 23, 29 through 32 all. For this one, you can just use the number of the postulate if it saves you time rather than writing the whole postulate out. The numbers are all in your book on page 73. And number 44. Okay, also do the next page of the MCAS questions, the 5 through 8.